All right, folks. First of all, thank you for attending this session. Today, we're going to be talking about building and deploying a live machine learning-powered music genre classifier. So, easiest poll for me of the day. How many here like music? Everyone, yes, of course, we all do, we all do. So I hope to see all of you all at Replay on Thursday. It's always a lot of fun. We also love music, right? We have singers, we have DJs. I kind of play a little music, but I'm terrible. But we all like, playing, and we like music. So we thought we'll do a fun little talk on how you can actually use data to build a model that actually classifies and tells you what genre and music file is. So let me introduce myself. My name is Sohan Maheshwar. I'm a senior dev advocate at AWS based in Amsterdam. And my co-speakers here are
Linda. I'm based out of Namer. I'm a developer advocate.
Hi, everyone. My name is Suman Devnath. I work as a developer advocate focusing around data engineering.
Yeah. So the three of us together are going to be talking to you about this entire process. Right? So let's get started. Imagine you are a DJ. Right? You're a DJ at a wedding. You're a DJ in a club. You want to keep that vibe going in the room. Right? There's a certain vibe. The crowd's enjoying it. You're also getting a lot of requests from people. And you really don't want to sequence like a disco track followed by a heavy metal track. That might bring the vibe down a little bit. So if there was a way for you to sort of get a sense of what the genre of the songs were, maybe you could sequence it better, right? So that's kind of what we were going for today. So in the next 30 minutes or so, this is what we're going to build. Number one, we're actually building a music classifier, which classifies music by genre. So when it gets an audio file, it tells you what genre it thinks the music file is. At the same time, we're building and training this machine learning model on AWS. So we will be doing a tech deep dive of that part as well. And finally, we're going to be deploying this model on an endpoint so that any app or a website or whatever could access it. And this will be fully automated as well, and it will be serverless. Right? So there are a lot of different components to this entire session. So stay tuned. The meta to this entire session also is, we have some data. How do you build a model and make an endpoint out of it? Or how do you get insights out of it? Right? So that hopefully these two things really come out through in the session. So let's talk about training a machine learning model. Now, regardless of how familiar you are with machine learning, you probably will know that any machine learning model is only as good as the data. Right? If the data is not great, your machine learning model typically won't be as good as well. Luckily, we're going to use a publicly available data set, which is a very good data set. It's called the GTZAN or GTZAN data set. So what this data set is it has a bunch of audio files, specifically in 10 different genres. So this is a labeled data set. And it has music files in blues, classical, metal, rock, all of that. There are 100 of each of these genres and 30-second clips of each of them. There is also a CSV file with some data points, which we will get to later. Why I like this data set is that there has been special consideration taken to make sure that it is not inherently biased. Yeah? So to give you an example, a lot of the popular jazz recordings from the 40s to the 60s might not necessarily have the best audio quality in terms of fidelity. Right? It was recorded 70, 80 years ago. In comparison, disco might have better fidelity because it was recorded in the last 30 or 40 years. A lot of disco music is electronically produced, so you might have higher fidelity. So this data set actually takes care of things like that. Right? So there are variances in audio qualities within the genres itself. So this way, if you upload like something of not great quality, it's not going to inherently bias towards jazz. Yeah? There are a bunch of other considerations in the data set as well, including representations of ranges of human voice. So for instance, rock, there are a lot of female singers as well, just so that it's not inherently biased there. The tools we're going to use for today, scikit-learn. So if you have dabbled in machine learning, you probably know that for any data analysis or machine learning training, you use the scikit framework. We're going to use something called librosa, which is specifically for music and audio files. So to get audio-specific information out of a file, we're going to use librosa. in this data set, there also is a possibility of training it with image representations of these audio files, right? And we'll get to that. And you could use TensorFlow to train that model. And we will be using certain well-known algorithms like k-nearest neighbor or SVM, which is support vector machines, to actually build the model, right? And we'll do a deep dive into that as well. Now, question for you all. Think of a popular song, like, okay, let's think of Ed Sheeran's Shape of You, not my favorite song, but how do you know that that is a pop song? Or how do you know when you listen to a blues song that this is a blues song? Even as a human, it's hard for us to articulate what makes a song in a certain genre, right? And that problem is even more difficult for a computer. So how computers actually figure out these genres are by using features of these audio clips as well. So we are going to extract those features, such as this, right? These features determine what the characteristic of that particular song or audio file is. So to give you an example, a spectrogram is a visual representation of an audio file which plots frequency over time, right? And the MEL spectrogram specifically does that for the range of human hearing. Similarly, a spectral centroid determines the center of mass for a particular audio file, right? Where is the energy of the song or around what frequency? We use Librosa to essentially get all of this data out for the entire data set. So Librosa is very simple to use. You just do something like librosa.load and ask for the features that you want, and it will just give it to you. It's actually pretty cool for us to compare and contrast like different genres of music. We randomly picked a hip-hop track versus a classical track, right? And this is, of course, not representative of the entire genre. We just picked 2 tracks. The first one that you see on top is a sound wave. It's just a 2D representation of a sound wave. So you see amplitude over time. And you see the hip-hop track has so much variance in amplitude versus the classical track. At the bottom, you see the MEL spectrogram of a hip-hop track. You can see the higher amplitudes at the bottom and the lower amplitudes on the top. Very different in MEL spectrogram for a classical track. Also, the other features that we get are the spectral centroid. As you can see in the hip-hop track, there is a center of mass located, and the brighter color that you see there are brighter sounds in the song, right? And in the classical track, you can see a lot more brighter sounds specifically. And any musicians here, or anyone who dabble in music? Few of y'all, yeah? So y'all might be interested in the one at the bottom. So essentially, it is a plot of notes or semitones against time, right? So in Western music theory, there are 12 semitones, so C, D, E, F, G, A, B, C, sharps and flats in between. So you see the representation of those changes of those semitones in the hip-hop versus the classical track, right? Unsurprisingly, the classical track has less variance because it's a lot more formal and a lot more structured, whereas the hip-hop track, of course, is a lot looser. Now, this doesn't mean that every hip-hop or classical track looks like this, but if you take this over a large set of data, similarities start to emerge, and that's what we're going to be using to build our model. Yeah? So using Librosa, we actually just extract this data for every track in our data set. So we extract length, but length is normalized for the entire data set. We extract the chroma mean, RMS mean, which is a representation of the loudness of a track. We extract beats per minute, spectral centroids, and so on. So all of this is collated into a CSV file. So we now have a CSV file with audio features for the entire data set, which we're going to be using to build the model. So my friend Suman will tell us how you can now use this data set to build and train a model using Amazon SageMaker. Suman.
Thanks, Sohan. All right, so a lot of physics so far in last 10, 15 minutes, right? Frequency, spectrogram, and all of that. So before we get started, Sohan mentioned that we are going to build a model to solve this problem, right? Which can help you to classify a music. So how many of you have worked on SageMaker or know SageMaker? Okay, quite a few. Okay, So before we jump into the demo, we'll just touch base on what SageMaker as a service is. So SageMaker is a managed service from AWS, which is kind of a, it is a family of services, because you can do a lot of things with SageMaker, starting from training, deployment, feature engineering, data labeling, and all of that. And we are going to see a few of them in our demo. Now, when we think about SageMaker, why you want to make use of SageMaker, right? So one of the things that you can do with SageMaker is you can do the training in multiple different ways. We are going to use a Jupyter Notebook on SageMaker to do the training, and I'll show you what are the benefits that you will get when you use a Jupyter Notebook within SageMaker with respect to a Jupyter Notebook in a virtual machine or on your desktop. So in SageMaker Jupyter Notebook, you get different kernels, like you don't have to install and manage frameworks like PyTorch, TensorFlow, Scikit-learn, and all of that. Everything is, you get that out of the box. So all you have to do is when you create a SageMaker notebook, you can select the kernel, and it's all ready for use. It also has a few of the built-in algorithms. So if you are into machine learning, there are different algorithms that we have, things like K nearest neighbor, logistic regression, linear regression, and all these algorithms are built in. That means all you have to do is you have to bring that data, and you have to just use that algorithm, and it is fine-tuned with respect to the infrastructure that we use behind the scene for training. So you get the best performance out of that algorithm. And one important thing here is this is something which is recently we launched. I mean, not that recently, in the last couple of years back. It's AutoML. So let's say you have a problem. Just like in this case, we know what is the problem, right? It's a music classifier problem. But let's say you know the problem, but you don't know which algorithm to use. So in that case, you can throw that data to AWS, and you can provide that input data and what you want to predict. These are the two things that you need to tell to SageMaker. And what SageMaker will do is it will automatically figure out what is the best algorithm, which are the best hyperparameters for your algorithm, so that you can just get started with that. Okay? And once it's not like whatever the SageMaker would recommend, you have to use it. You can always change those hyperparameters, change the algorithm, change the code, but you get it in the first place. The other thing is when you do ML training on SageMaker, you don't have to think about the scale, right? So because let's say if you have to do a training on-premise or on a virtual machine, you need to know how many GPU, CPU, and how much capacity is needed for your training in the first place, right? But just like everything in our life, we cannot predict all of that because data keep on increasing every passing day. So with SageMaker, you don't have to buy that hardware in the first place. All you have to do is when you start the training, you can just provide how many instances you want for that training to happen. And under the hood, SageMaker will create containers, that many number of containers for your training job. And let's say that training job runs for 10 minutes. After 10 minutes, all those infrastructure get destroyed. So there is no CapEx cost as such when you go with SageMaker machine learning. So let's jump into the demo, and we'll show you how you can make use of Jupyter Notebook. Yeah, that's OK. Thank you. All right. So this is the SageMaker console. So if you have never come to this a dashboard, this would be the welcome screen then when you come to SageMaker. And if you see, on the left-hand side, you see a lot of different options. So there is notebook. You have processing, where you can process your training job. There are different algorithms. These are the training jobs, hyperparameter tuning. This is for inference, that is after deployment. You can make use of SageMaker for creating the endpoints. But today, we are going to use a simple model using Jupyter Notebook. Okay, so this is a Jupyter Notebook that I have created. So if you want to create something like this, all you have to do is you have to click here and create a notebook. And you can provide the instance type, because under the hood, it will create a container for you for this notebook. That's all. So once you create that, you just click on this and click on Open Jupyter. Okay. So this is the window that you will get. I have created one folder. That's why you see this here. Now, this is very much similar to the Jupyter notebook that you might have seen, if you have used that. But the special thing that you see in SageMaker Jupyter notebook is SageMaker examples. So you can come here and you can see all these different algorithms which I was talking about. These are the built-in algorithms, and you can just see them, use them, edit them, and make use for your business problem. So first, what you have to do is you can get inside. I have this notebook created, but if you come to New and click here, you will see that these are the different kernels. Like you have kernels for PyTorch, Spark, then MXNet, and all of that. So you don't have to install, configure all these, third-party packages, right? All these kernels are readily available the moment you create a SageMaker in a notebook instance. All right, so I have this notebook opened in another tab, so I'll just switch to that. So let me just quickly go over what we are going to do. So we have imported a bunch of libraries here, NumPy, Pandas, because we are going to train a model using this data set, which Sohan just mentioned. And this is a classification problem because we know that there are only 10 genres in this data set. And we need to convert that music files into vector, right? Or into an array of numbers. So Sohan earlier mentioned that this data set comprises of two different types of data. One is in the audio file, one is in the text, a text file. What we are going to do now is we are going to see how this audio file would look like, right? So all this data is there under this folder called dataset. So if you come here, we have a dataset folder, and inside there are two different formats, right? So we have an audio format, and inside this we have different folders, and inside that we have the songs of respective genre. So what we are doing here is we are just mentioning the data path, and then we are just loading using Librosa, okay? Right? So this is the library which you can use to convert your audio file into text. Because at the end of the day, what you really want to do is you need to convert that audio file into a vector of numbers, right? So once you load that data, if you then print that vector, if you see this, when you run librosa.load, it returns a tuple which comprises of the vector and the frequency. So if you see this, the vector is quite long, right? If you see the size of this vector, it's around 600,000, array of 600,000 numbers. Now, if you are into machine learning, you can now condense that using some technique like you can use t-SNE or PSA, principal component analysis, which can shrink down all those 600,000 columns or features into smaller number of important features, right? So, but for now, we are not doing that. But the idea is to convert that audio file into a text format. And then you can actually use Librosa to display, to show you the graphs. So if you see this, this is the frequency graph which Sohan was mentioning earlier in the day. So you have the time axis in x-axis, and you have the frequency on the y-axis. So this is about the audio file. But as a data engineer, once you have this vector, you are done, right? So once you convert that data set into a vector of numbers, then you can use any algorithm to start your training. So now let's talk about the text file. The text file is pretty straightforward. We have a dataset.csv, and if you see this, it has the the music file name and all these different features. And if you see this, these are the different features that we have. So we don't have to know what feature is what. As a machine learning engineer, you may not know, right, that what this particular column is talking about. Although it's good to know, but for a machine learning engineer, these are just the features, right? So let's do some analysis on this data. If we do df labels .unique, we can see the different genre of the data set, and we have total 10. But these are in text format, right? If you see this here in the last column, the labels column, these all are into text, right? Blues, then jazz, and all of that. So we need to convert that into number, right? So that's what we are doing here. So we are just categorizing that into category, and then we are taking the code. And then we are creating this dictionary as a hash where each number belongs to a different classifier. All right, so once we have this data, what we need to do is, before we start this training, from that data, we need to remove that class labels, right? Because for training, we will not provide the class labels, right? So that's what we are doing here. If you see, we are just taking, there are total 61 columns, and that 61 columns, if I scroll, that 60th column and 61st column contains the class labels. And this number I just added just to convert that into numbers. But now we don't want these two. We will save that in a separate data frame. So that is what we are going to do here, right? So we are just going to take from the first column to the 59th column, okay? So once that is done, we can split the data set into training and testing. That's what we do in any machine learning problem. And so that we can save some data for testing after the model is trained. So we are keeping just 20% of the data for testing. And before we start using the training, we need to normalize that data. And why we need to normalize this data? Because we have 60 different features, right? And all these features might vary from, let's say, a decimal point to a huge, large number. So for any machine learning training, before you start the training, you need to normalize that. So you need to convert that number, data into maybe 0 and 1, so that all these features spans between 0 and 1. So now we are going to use this algorithm called k-nearest neighbor. So if you're new to machine learning, what this k-nearest neighbor is about is, if you look here, there are two different classes of data, green and red. And we have to identify what this black point belongs to, whether it belongs to green class or red class. So what k-nearest neighbor does is, depending on the value of k, it will try to find the nearest class of that number. So it will see that if I have to pick 5 neighbors, out of 5, 3 neighbors are green and 2 neighbors are red. So I will classify myself as green, right? So that's the idea about k-nearest neighbor. So this is in XY dimension. It's in 2D. But in our case, this is going to be in 58D, because we have 58 features, right? But we cannot visualize that here. But just to give you an intuition, how this k-nearest neighbor works. So that k belongs to how many neighbors that you want to classify. So we have come to a conclusion that after a lot of testing, which I have not shown here, that k equal to 5 gives us the best result. But you have to play around with this number to get the right k for your problem. All right, so to do a training, it's pretty simple. I'm going to use scikit-learn for this. And I have imported this in the first place, in the first cell. If I scroll back, I have actually imported this from scikit-learn. Okay. So now if I scroll down, I will do the training as knn fit, and I will pass on the our data set, that is xtrain, and ytrain is the labels. And then I can see what is the performance, right? So this is the accuracy, 89%. And now what I can do is simply I can do some testing. So I have some test data set called test.csv, and I can simply do knn.predict, and I can see that the prediction. So if you see this, there are 5 songs, and it has rightly predicted. The actual class is metal. The predicted class is also metal. So this notebook is available in the GitHub repo, which I'm going to show you later. But you can always play around with this notebook. All right, so now what we do. So as a machine learning engineer, I have trained this model. So next thing I need to do is I have to save this model somewhere, right? Because ultimately we need to deploy this model. So I'm just saving this model into model.p file into my local notebook, and then I am actually uploading this into an S3 bucket, right? So that's all. So that's all I'm doing. I have trained this model, and my model is saved into model.p file. So if I come here, you see this model.p file, and this model.p file I'm just uploading into an S3 bucket. That's all I'm doing, okay? So as a machine learning engineer, I am done with my work, right? So I don't have to do anything. Now I don't know how this is going to be deployed, and that is exactly what Linda is going to walk us through.
Awesome. Thanks, Uman. Yeah. So we have our machine learning engineer. We saw the building and the training of the model, right? But how do we get it available to the outside world? So I'm going to come in as the app developer, and we're going to deploy this to the outside world. So what are we going to build? We have our musician, our DJ, our end user, okay? And we want them to be able to send song information to the cloud. And what we want the end user to receive is then the genre prediction. And so Suman already spoke about building and training the model. And what we're going to focus on is the inference and prediction on AWS Cloud and how we're also going to get the model up there into the world. But what tools should we use to build this? Okay? We could use servers. We could have to consider a lot of things. What size are the servers? How many servers should I budget for? Could maybe spin up an Amazon EC2 instance, right? But there's a lot of things to worry about. And I don't know about you, but I think I want to just focus on the business problem and not have to focus on the operation and maintenance of it. So the other way to approach this is serverless. And serverless is an architectural approach of least possible ownership, right? It does not mean no servers. Serverless just means that you, as the developer, do not need to maintain those servers. It's an abstraction layer. And one of my favorite analogies is this. You have a house, and maybe you want some water for your house, right? You might need to spend money on it, dig the well, check the water, do the plumbing, right? A lot of work. Or you can tap into the city water and just pay a fee for what you use. And essentially with serverless computing, that's the same idea. You are pretty much, except in this, sorry, I'm going back. Woo! Okay, in serverless computing, this is the same idea, except the water is maybe your CPU and memory, right? So when we think about serverless services, tongue twister, serverless services, a lot of times one of the main services is AWS Lambda, and in this use case that we're going to use. And that's serverless cloud computing. And the beauty with this is you as the developer only need to worry about your code. You don't need to worry about everything around it. You just need to worry about your code. And the main takeaway is this is event-driven compute. Something has to trigger it. As opposed to if you would use servers, you would have to have it running all the time. This is just triggered, and you have, it runs only, and you pay for what you're using, right? So how are we going to see this in our architecture? Let's look at our use case, right? We just talk about what we're going to build. And so here we have our client, which is our musician, DJ, and they send maybe a song name or the song information to Amazon API Gateway, to an endpoint. And Amazon API Gateway is actually one of over 200 AWS services that can trigger a Lambda function. And in this Lambda function, we are going to have code that will be written in Python. There are many runtimes that supports, but we're going to have it written in Python. And we want to inference that machine learning model we spoke about, right? And we're going to inference it from EFS. But here's the thing. How are we getting it to EFS? Simon, what is EFS? And didn't you say you were going to download it to a local Jupyter notebook? I don't know.
Exactly.
Yeah.
So just a while back, I have uploaded that model into S3, right? But here, in this architecture, we see that the inference is happening for EFS. So why EFS? So EFS is an elastic file system on AWS, and it's kind of a network-attached storage. And I'm going to show you why we are using EFS. But as a machine learning engineer, what we will do is we will upload that model into S3. And that's exactly what I did during my demo. But the moment we upload this, we will have another Lambda function which will get triggered, and it will load that data into Amazon EFS. And why we are doing this? there are a couple of reasons. One is separation of concerns. So machine learning engineer can work independently without knowing about the production. And we can build the intelligence inside the Lambda function to pick the production-ready models, not all the random models with which the machine learning engineer might be training for testing, right? And the second advantage of using EFS in this case is when the inference is happening, the instance where this Lambda function is running, it is going to talk to the model natively using a native API call, right? So it's just like reading the model from the local drive. Whereas if I make that Lambda function read the model from S3, it will be an HTTP API call, right? And you will be charged for every HTTP GET request. And that we don't want, because we know that when we deploy the model for production, there might be hundreds and thousands or even millions of inference happening. So if you use EFS, that cost you will cut down, because all those API calls will be local to the instance where this Lambda is running. So essentially, once the Lambda function gets that model and performs that inference, you get the prediction to the client. So the DJ or the application end user will get that prediction. So if you look around, to summarize this whole architecture, we have two applications. One is app1, which is a Lambda function which gets triggered by an S3 upload. And there is another application called app2, which gets triggered by the end user or the DJ. So now, Linda, we have 1, 2, 3, 4, 5, 6 services. How we are going to do this?
I mean, we could do it manually. I don't know about you, but this could get quite hard to maintain like that. I don't know. We could do it manually, or we could use something called SAM. And before I get into what this very cute little squirrel is, by a raise of hands, how many of you have used CloudFormation? All right, quite a few. So CloudFormation, right, it's a way for you to have like to not have to manually deploy, right? You can provision and manage your services in an automated way. It's a blueprint. And so SAM is an extension of that, but for serverless, okay? And so the beauty here is what you could write in 100 lines with SAM would maybe take you 800 lines with CloudFormation, especially for serverless architectures. And as you can see here, we could list all our resources. Don't worry about zooming into the code. We will demo this in a moment. But you really could do it in a shorter way, and everything that we talked about could be spun just with that. So how about we get building, right? So if you want, you could use this QR code to see the GitHub link that we're going to use, and I'm going to demo this. OK. So right now, I'm going to use Cloud9, but you could use your local environment. And what we really want to do is we want to start creating the SAM template and make all this architecture for our musician or DJ. And we're going to start with making a directory. We're going to make a folder in Cloud9. If you're using Terminal or anything else, whatever you prefer, we will call it, naming stuff is always what takes the longest. Let's call it BOA322, because that's our session. And maybe like ML SAM project. All right. And then we're going to CD into this. All right. And now what we will do next is maybe we want to check that we have the AWS CLI, right? AWS version. Good. We have our CLI. Next, we want to check if we have our SAM CLI, because this is what we'll need. If you're doing it locally, you might need to install it. And one more thing, we probably need to check if we have our credentials configured. So, right, we could do AWS, S3, and LS, and just see that it's listing something and connecting, right? So we have that working. Great. And how we start out with SAM is we have to initialize it. So the way to do that is SAM init, right? SAM init, and then it will start provisioning it. So you could then put a path here. We want to be able to give it code. We have a GitHub repo that has all the code that we just showed you in the architecture. So I'm going to use that, and I have it open right here. So I could just do, if you have it in a repo, you could just do choice 2, and then you could give the path of the GitHub repository, right? Sorry about that, pasting here. All right, so we are going to actually get it locally here. So I just initialized it, and when we initialize it, we could see it coming up here, right? It was empty before, and we have it all coming up here. So the next step would be that maybe we could take a look at the template that it downloaded, right? So in a SAM template, how does it know that it's SAM, right? It's in CloudFormation, right? It really just translates everything into CloudFormation under the hood. So the way it knows it is the first 2 lines. It reads from top to bottom. And the first 2 lines have AWS : serverless. So that's how you know it's SAM. And usually in our SAM template, we have 4 different sections: global, parameters, resources, and outputs. With global, global is pretty much like defining a global variable, right? Anything you're reusing. And so here, one of the variables we are calling is the model's path. And the reason we're doing that is because in our architecture, if you recall, right, I'm going to pull this up, we were using 2 Lambda functions, right? And we have these 2 Lambda functions, and they both need to use that same path. So that's a good place to define it, right? You could define it in the global parameter, the global section, and then you could reuse it throughout your template. So that's globals, right? The next section we could look at is parameters. Now, parameters is really cool because we have the S3 bucket that we created, right? And the S3 bucket is something that you name when you deploy, right? You're naming it. So how does my template know what the name is? It knows it because you could put it in parameter and it will append it to the actual template. So here you could put the name of here it's in parameters, the name of the S3 bucket, and then when you reference it, you'll be able to append the name that you pick in your deployment. But the most important part is the resources, right? That's where we list everything that we had in the architecture. All right, so here we have our S3 bucket and all the different services that we need. And we're not going to go through all of these, don't worry. But the S3 bucket is where we're going to have the ML model and that you could upload. But the main thing I want to go to here is the 2 Lambda functions that we discussed. So we have ML model upload function, right here. Sorry about that, I'm going to minimize it so it's not. OK, we have these 2 Lambda functions. So just like we have in our architecture here in our photo, just going to pull this up, right? We have these 2 Lambda functions. OK, we're pretty much saying everything here in our resources. And I want to take a look at 2 things here. The ML model upload function, if I open it up, right, you could see here that it says depends on mount target A, right? So why does it say that? We said that SAM reads top to bottom, right? Why does it say that? Because it's asynchronous, meaning if you're uploading that model, you need to make sure EFS is there so you could actually mount it. So if you don't say depends on mount target A here, it's going to fail. So in this function, we need to make sure that's there. And then in the next one, if you look here, oh, sorry, let me just open this. All right, so here we also see a runtime of Python, right? And we're putting all the different like runtimes and all of that. But if I look at the next Lambda function here, which is the one that's responsible for running the Python code and inferencing from the model and the deployment end, OK, here, where does it say language? Do you see the language here? Oh, sorry, right here. Do you see any language? No, it says image. Why? Because Lambda could be deployed in many ways. If you go to Lambda right now and you try to create a function, you will see you have 3 ways here. So one of our Lambdas was created by a container image, and the other maybe from scratch. So that's why we just define it differently in the SAM template. All right, so the last section we have here, we looked at our resources, right? And also one more thing. Yeah, we're good on time. We have all these other resources here that you see in between the S3 bucket and the Lambda functions, and that's all for EFS, because Lambda functions by default do not need a VPC, right? They don't need a VPC, but EFS needs all these different things, right? These subnets and everything else. So we have like all these resources in between. Might look like a lot on a page, but it's all for EFS to work. Awesome. So next step, anyone know what the next step is? Next step is we want to actually build this container. So to do that, I'm going to go back to Cloud9 and view my terminal. Here we go. And I now want to build this. Right now it's just local. Okay, we initialized it, but we need to actually build it. So SAM build, use container. Today I have typos. Oops, sorry about that. And And what we're essentially doing is we need to build it locally so we could deploy this, right? And this takes a moment, but that's OK. I do have a folder that I already deployed, because we're not going to wait for all of this to deploy. But what I want you to see is actually the next step. So once this is done, we have this container that helped us build it. And now we could actually, it kind of shows you in SAM different things you could do. You could SAM validate, right? SAM validate to make sure your SAM template is actually valid. And then the most important part, we can now SAM deploy. And now we could actually just say, hey, please deploy all of this, right? So we are going to do deploy guided. All right, and so here you have to name your stack, right? And that's going to come into CloudFormation. So let's say we're going to call this SAM app BOA322. I don't know. Final. There we go. OK, US East 1. And here we have our parameter. Remember our parameter from the SAM template? Well, this is where we define the name, and it will append it to that SAM template. So we could call it, I mean, it has to be unique, but we could call it, we'll just call it the same thing. And then you could kind of keep default for the rest of it. There is an area that, because we're doing this on talk, right? But what's really cool is you could just deploy all of it from here, and you'll have it running. So let's see. Now it's going to run. And I'll now show you what it looks like once you have everything deployed. So once you have everything deployed, you could go over to API Gateway. And if you see here, we could actually test on our GitHub link that we shared. We have all the steps here that we were talking about regarding initializing and all of that. And we have here a sample song name that you could use from the actual data set that Suman spoke about. We have a sample song name, and we could actually take this and test it inside the UI. So this API gateway was, right, this API gateway was from here. I'm just going to pull up the photo here, right? It's our lovely friend, Amazon API Gateway. And we have it right here. And if we want to test it, you could go here and test it locally in the UI, not locally, but in the UI. Let me just delete this. All right. And if I press test, hopefully this gives me the output of the genre. Oh, wonderful. We have blues. And so from there, you could kind of also build a front end with it and create something nice and be able to use it from there and add layers to this. But we could see that it's working. We see that it's all deployed. One more thing to mention. In our SAM template, we saw that we also have outputs. And as you see this going, outputs is what you want to see when you, let's say, run the deploy. We want to know what our API endpoint is, because let's say I want to build a front end with this, right? So I want to know what that URL endpoint is. So we could actually say here in outputs, this is our API gateway endpoint for prod stage, and then we could go into that. And with that, Sohan, I'll invite you to take it away. And let's see if I know how to work this thing. Nope. There we go.
There we go. All right. Oh, yeah, it is. Yeah. So just to recap everything that we did, we had a data set. Then we built and trained a model using SageMaker. We hosted that model on S3. And then, of course, we used SAM to build out this entire end-to-end. We did plan on playing like live popular music to see if the model works, but turns out copyright law is a thing, and that we're not allowed to do it. But you can actually deploy this at home and maybe try it out with like 30-second clips of popular songs and actually see what the model says. It could totally work. For some next steps, do look at the GTZAN dataset. I'm assuming a bunch of people here are interested in music. So there are a lot of cool things you can actually do with this dataset and the data it provides. But also look at the entire journey that we sort of described today. We went from a simple dataset to something that potentially could be used in production because of the use of things like API Gateway, EFS, and S3. Right? And of course, we automated the entire thing as well. So very production ready if at all you all wanted to do so. All of these example notebooks are also available online. So do check it out, play around with it. And we have some SageMaker workshops too you can do. For me personally, sometimes the machine learning aspects are very hard, and SageMaker takes care of that for you. Right? So you can run like a KNN algorithm, you can run an SVM algorithm, and SageMaker does that hard work for you, and you don't have to do too much mathematics, which I'm not great at. Anyway, I hope you learned something new today. Thank you so much for this. And yeah, we're around here. If you have any questions, we can take them offline. Right? And we do have swag, some badges that you can use.
AWS developer.
Yeah, you can collect it. Thanks again. Do fill in feedback. And yeah, enjoy the rest of reInvent and replay, more importantly. All right, thank you.